Okay, so far in this unit we've been talking about the concept of acceleration, and in the last video we solved acceleration problems using our three equations for constant acceleration. Okay, so what we're going to do to wrap up this unit is we're going to look at solving problems that involve acceleration with motion graphs. And we kind of did this in the last unit when we did some calculation questions with the constant velocity equation, and then we looked at some graphing problems that involve constant velocity. Okay, so we've already seen two types of graphs before. We've seen position time graphs and we've seen velocity time graphs. And just to remind you, when you're dealing with constant velocity, roughly what that looks like is this. Okay, so a position time graph, which I'm going to label xt, if you have constant velocity, the shape is going to look something like this. It's going to be linear. And remember that the slope of a position time graph represents the velocity of the object. Okay, the velocity time graph, again, only for an object at constant velocity, would look something like this, with the velocity not changing. Okay, and so that's basically the two types of graphs that we saw in the last unit. Now, this unit we have added acceleration. And remember that by definition, an object that is accelerating is changing its velocity. Okay, and so what we're about to see is actually these graphs change shape completely based off of whether or not there is acceleration. Okay, I also want to remind you that because acceleration by definition means that your velocity is changing, constant velocity and constant acceleration, those two things cannot exist together. Okay, you either have one or the other. Either you have motion with constant velocity or you are accelerating. Okay, you can't have both at the same time. That's not possible. Okay, so let's take a look at a simulation to get a sense for how these motion graphs change once you go from constant velocity to constant acceleration. Okay, so we're going to take a look at a simulation, and I'll put the link up so you can play with it yourself. Okay, so if you open up the simulation and you click on charts, you can adjust the position, velocity, and the acceleration of the moving man on the left side. And I'm going to just remove these brick walls so the moving man doesn't stop. Okay, and so just to show you how these graphs look like if you just have constant velocity, I'm going to show you what the position time graph and the acceleration time graph look like with constant velocity. Okay, actually, let me change it. Actually, let me increase the velocity a little bit more. So let me make it 1 meter per second. Okay, so this is with constant velocity. Okay, the velocity is positive. It's constant at 1 meter per second. You can see how the velocity time graph is horizontal. Okay, it's flat. And the position time graph is linear. Okay, and the velocity being positive means that the man is moving in the positive direction. Okay, so take a look at the shapes of these graphs. Now again, just to show you one more time with constant velocity, let me show you what happens if I give the moving man a negative velocity. Still constant velocity though. Okay, so notice our position time graph. It is going down, but the shape is still linear. Remember, the slope of a position time graph represents velocity. And so notice that this graph has a negative slope. And if we were to calculate the slope, it would be the same as this value on the velocity time graph, which is -2. Okay, so this should not be anything new. We've seen these two types of graphs before for constant velocity. Okay, so now I want to show you how the motion graphs change when we add acceleration. Okay, so I'm going to add an acceleration of 1 meter per second squared, and we're going to see how the position time graph and the velocity time graph change. Now remember, 1 meter per second squared means that the moving man is going to increase his velocity by 1 meter per second each second. Okay, so watch how the shapes of the position time graph and the velocity time graph change. Okay, and if you actually look at the moving man, you can see him going faster and faster and faster. Okay, now he's off the screen. Notice that the position time graph is no longer linear. Okay, it's actually curved. And in fact, this is a type of curve that you've seen before. This is a parabola. Okay, you should have learned about parabolas in your previous math classes. Okay, like a quadratic. Okay, the graph is a parabola, or what you would call parabolic. The velocity time graph, notice, is now linear. Okay, because the velocity is increasing, but it's increasing at a steady rate because the acceleration is constant. Okay, and so the shapes of the graphs have changed completely. In other words, just looking at a graph, you should be able to tell whether or not an object is moving at constant velocity or whether it's accelerating. Okay, just based off of the shape of the graph. Just to show you one more time, let's see what happens if I have a negative acceleration. Okay, so I'm going to have an acceleration of negative 2 meters per second squared, and we'll see how that changes the shapes of the graphs. Okay, so now I have an acceleration of negative 2 meters per second squared, and again you can see the position time graph is no longer a parabola, or it's no longer linear, it's a parabola. Okay, it's just a decreasing parabola now. And the velocity time graph is no longer horizontal, it's actually linear. Okay, so you see now with your own eyes how the position time graph and the velocity time graph change, whether or not you have motion with constant velocity or motion with constant acceleration. Okay, and so that's what we're going to talk about now in the notes. Okay, so on this slide right here, you can see the side-by-side comparison. Okay, on the left side, you can see with constant velocity how the position time graph and the velocity time graph look, and they're just how we described them before. When you go from constant velocity to constant acceleration, the position time graph becomes curved. Okay, it becomes a parabola when you have acceleration, and the velocity time graph goes from being horizontally flat to being linear. Okay. So again, you should be able to look at a graph and recognize whether or not the object is moving at constant velocity or whether it has a constant acceleration based off of the shape of the graph. Okay, you're expected to be able to interpret graphs like that. Okay, now you also need to know some other facts. Okay, so here's what you need to know about position time graph and velocity time graph for motion with constant acceleration. And again, I would recommend that you add this information to your notes. So, with an object that has constant acceleration, the position time graph is going to be a parabola. That's what this word parabolic means. That means the shape is a parabola. Okay, we saw that on the moving man simulation. The y-intercept still represents the starting position of the object. The slope does still represent velocity, okay, but because the graph is curved, you can't actually calculate the slope on a position time graph. In order to do that, you would need calculus, which is more complicated math than you need to know for this class. Okay, the velocity time graph, if you have acceleration, is going to be linear. The y-intercept represents the initial velocity of the object. The slope represents the acceleration of the object. This right here is a key piece of information on this slide because we saw when we talked about position time graph, the slope on a position time graph represents velocity. Okay, the slope on a velocity time graph represents acceleration. And the reason for that is, remember, slope is like a rate of change. And so acceleration by definition is the rate of change of velocity. Okay, so the slope on a position time graph represents velocity. The slope on a velocity time graph represents acceleration. Okay, which means if I give you a velocity time graph and I ask you to calculate the acceleration, you would find the slope for that segment of time. Okay, so pause it here if you need to write this down. Okay. Okay, there's a chart right here that you should be familiar with. Normally I would just write in the chart. Okay, but here are the answers. Really though, it should say parabolic and not curved. Okay, so I'm going to change that. Again, parabolic just means the shape is a parabola. Okay, so make sure you have this down in your notes. This is everything you need to know about motion graphs. Okay, so what we're going to do now is we're just going to do some examples solving problems with motion graphs. But everything you need to know about solving problems with motion graphs comes from this slide. Okay, so let's go to example 1. Okay, so example 1 says, look at the velocity time graph shown to the right. When you're looking at graphs, always make sure you know what type of graph you're looking at. Because if it's a position time graph, you might solve it a completely different way than if it's a velocity time graph. Okay, so the first question says, during what time interval is this object traveling with a constant velocity? Okay, remember on all of these graphs, time is on the x-axis. So when it says what time interval, it's asking for the x values from this x value to this other x value. Okay, in math terms, it's asking for the domain. It's asking during what domain is this object moving with a constant velocity. Okay, so this is a velocity time graph, and remember, constant velocity on a velocity time graph looks like this. Okay, it looks horizontal. Okay, because if it's constant velocity, that means it's not changing. Okay, so the answer to this question would be the time interval for this segment right here where you have constant velocity. By the way, the question also says what velocity is this? That velocity, if you read off the graph, is 8 meters per second. Okay, now to answer the question is asking for a time interval. Okay, so if you look down here at the x-axis, it's moving with a constant velocity from 4 seconds right here all the way to 10 seconds. Okay, so I would answer this question by saying from t equals 4 seconds to t equals 10 seconds. Because it's asking me for a time interval. Okay, that's the time on the graph where the object is moving with a constant velocity. Okay, and again, I know that just from the shape of the graph. Now the second question says, during what time interval is this object accelerating? So remember, on a velocity time graph, acceleration looks linear because acceleration means how fast your velocity is changing. So where is the velocity changing? Well, it's changing from here. Okay, so from t equals 0 seconds all the way up to here, to t equals 4 seconds. Okay, so that's how you would answer the second question. Now the second question also says to calculate the acceleration. So remember, position time graph, the slope represents the velocity. Velocity time graph, the slope represents the acceleration. Okay, just think slope is rate of change and acceleration tells you your rate of change of velocity. So if I want to find the acceleration here, I need to find the slope. Remember, you pick 2 points that lie on the graph. Okay, so I'm going to pick the endpoints, 0, 0, and then this is 4, 8, and then I just use my equation for slope. Slope is y2 minus y1 divided by x2 minus x1, and I plug in my points, and I find that the acceleration is 8 divided by 4, so a equals 8 divided by 4, which is 2 meters per second squared. Remember, acceleration always has the unit of meters per second squared. Okay, so that is example 1. If you need to take a closer look, pause it here. Okay, so I'm going to erase this. Example 2 says, first of all, what type of graph is this? Okay, so always look on the y-axis. Okay, if it has an x or if it says position, it's a position time graph. So this is a position time graph. Okay, so that's what I would just say here. I would just say this is a position time graph. The second question says, which of these 4 objects is moving at a constant velocity? Now remember, on a position time graph, constant velocity looks linear. Okay, so which of these objects, or which of these graphs look linear? Well, that would be A and B. How do you know? Because they are linear. Constant velocity on a position time graph looks linear. Which of these 4 objects is accelerating, and how do you know? So remember that the position time graphs turn into a parabola when you have acceleration. So C is definitely accelerating. D, if you look right here, D has a little bit of acceleration. And so what's happening here is the object is not moving right here. The object is at rest. Okay, the slope is 0. So not moving, not moving, not moving. And then right here you can see this little bit of a curve as it starts to move, and then it's moving with a constant velocity after that. Okay, so if it goes from not moving to moving, there has to be some acceleration to make that happen. Okay, so I would say C and maybe part of D. Okay, so D is a little tricky. Okay, there is some acceleration in there. Okay, so that is example 2. Again, based off of the shape of a graph, you should be able to answer the question of what type of motion is it. Is it constant velocity or is it accelerating? Okay, those are your two options for motion. Okay, so let's do a few more examples. Okay, example 3 says, what type of graph is this? Okay, this is a velocity time graph. You can tell because it says velocity. And then it asks us to calculate the acceleration from, and then it gives us 3 different ranges. Okay, so from 0 to 3 seconds. Okay, so here's 0 seconds, here's 3 seconds. So this is the first range. From 3 to 5 seconds is from here to here. And then from 5 to 8 seconds is from here to here. Okay, so there's basically 3 segments and they want us to find the acceleration for all 3 segments. Now, a couple things. Remember that on a velocity time graph, acceleration makes the graph look linear. Constant velocity makes the graph horizontal. Okay, so I can tell right away that if the velocity is not changing, that means there's no acceleration. Okay, acceleration tells you how fast your velocity is changing. If your velocity is constant, there is no acceleration. It's automatically 0. So I can tell right here, not only is the velocity not changing, it's actually not even moving because the velocity is 0 here. Okay, and it stays at 0 for 3 seconds. So the object's not even moving for the first 3 seconds. So from 0 to 3 seconds, I would write A equals 0 meters per second squared. Okay, the slope here is 0. And so that's how you can tell it's not accelerating. Now, from 3 seconds to 5 seconds, to find the acceleration on a velocity time graph, we need to find the slope. Okay, so I pick my 2 points. I'm going to choose 3, 0, and then this point up here is going to be 5, 8. You can pick any 2 points you want as long as they lie on the graph. My equation for slope is y2 minus y1 over x2 minus x1, and I plug in my points. I do 8 minus 0 divided by 5 minus 3. So that gives me 8 over 2, which is 4. Okay, so from 3 seconds to 5 seconds, my acceleration is 4 meters per second squared. In other words, every 1 second that passes, the velocity increases by 4 meters per second. Now, what happens after 5 seconds? Well, you can see that the graph goes horizontal again, meaning that you have constant velocity. So right in here, during this last segment, from 5 to 8 seconds, the object has a constant velocity. So by definition, that means the acceleration is 0 meters per second squared. Okay, and then the last question says, during what time period is this object moving forwards? Moving forwards means positive velocity. Okay, so during what time does the object have a positive velocity? Well, the velocity is always positive. Okay, even over here when the graph is decreasing, the numbers are still positive. Okay, they're just getting smaller. So I would say from t equals 3 seconds to t equals 10 seconds, the object has a positive velocity, and so it's moving forward. Okay, don't confuse negative slope with negative velocity. Okay, so here the graph is decreasing. The slope is definitely negative because the graph is going down, but the actual values are still positive because it goes from 8 to 7 to 6 to 5 to 4 to 3, but those values are still positive. Okay, so let's see if you can do the last 2 on your own. Pause it here if you need to finish writing this down. take a look at example 3.5 and see if you can answer this on your own. Which of the position time graphs shown represents an object that is accelerating? Okay, so hopefully you answered this question correctly. The correct answer should be D. Okay, for A, this object is not moving because the position is constant. Okay, or you can think like the slope of this graph is 0. This object has a positive slope, so this object is moving forward, but it's moving forward at a constant velocity. And I know it's a constant velocity because the shape is linear. It's a constant velocity. Object C is moving backwards, and I know it's moving backwards because the position is decreasing, or you can think of it like the slope is negative. Okay, remember, position time graph, the slope represents velocity. Okay, this is also constant velocity because even though the graph is going down, the shape is still linear. Okay, so the correct answer is D. Okay, pause there if you need to look at that. And let's try to do one more example. Okay, so see if you can answer all 3 questions for example 4. Okay, there's 3 questions. During which segment is the object moving at a constant velocity? During what segment is the object moving at a constant acceleration? And then it says to calculate the acceleration of this object. And just to be clear, because technically there's 3 different accelerations, let's say for segment A and B. Okay, so see if you can do example 4 on your own, answering those 3 questions. Hopefully it's pretty straightforward. Okay, so the answer to the first question, the object is moving with a constant velocity, segment B. This is a velocity time graph. Remember, constant velocity looks like this on a velocity time graph. Acceleration looks linear, okay, or at least not horizontal. Okay, so the answer for this should be B. The answer for this should be A. C kind of looks linear. It's not completely linear, but it does kind of look linear. If I had to guess, I would say C has some type of acceleration, but I don't think it's constant because this is even starting to curve a little bit, maybe. Okay, so if you said A and C, you might be okay. A is definitely constant acceleration, though, because A is definitely a straight line. And the last question says calculate the acceleration of the object for segment A and B. Segment B is easy because if it's constant velocity, the acceleration is automatically 0 meters per second squared, right? Because the velocity is not changing, and also the slope of the line is 0 because it's flat and horizontal. For A, okay, velocity time graph, to find the acceleration, you need to find the slope. You pick 2 points. Okay, so I'm going to do 0, 0, and I'm going to pick this endpoint over here, 20, 40, and then I plug into my slope equation. I'm going to do 40 minus 0 divided by 20 minus 0, and that gives me 40 divided by 20, which is 2 meters per second squared. So the acceleration in segment A is 2 meters per second squared, and that is the answer to example 4. Okay, so after watching this video, you should be able to draw and interpret and do calculations with motion graphs with both constant velocity and constant acceleration. Okay, you should now be able to work on your practice problems involving motion graphs, and then we are done with this unit. As always, please let me know if you have any questions, and I will see you guys in the next video.